Hello students, today we are going to learn a technique to solve the problems. I have picked a very simple problem. Our problem is telling me that a particle is moving along some axis like x-axis and a dragging resistive force is acting opposite to it. This force is proportional to its instantaneous velocity. Okay, so it is given as minus k m v to the power n, where k is positive constant, m is the mass of the particle. So what we are going to find that the particular distance at any instant of time and its velocity at any instant of time. Okay, so that is our goal to find that. So let us solve it one by. So it is very special case I have it, but it can be more surprising when you will see that if I vary the power of v in the force, then the result will be different for different cases. So for the first, I have picked uh, the first case is I have picked here. That is case number one when n is greater than one. Okay. So suppose the more simpler case one f equal to minus km is v to the square. Okay. So let us do this. So if I apply this, so we have to find the instantaneous velocity at any instant of time and the position of the particle at any instant of time. So there are two cases, two solutions of this equation. And for two solutions, we have to pick two initial conditions. So at t equal to 0, we have, take, we have taken that the position of the particle at x equal to f naught and its velocity equal to u. So let us solve it. Let us solve. So solve is, I'm going to write the first f equal to minus this kmv square and writing f equal to ma. Ma according to the Newton's second law, where the mass is taken to be constant because it is a point particle. So m cancel out. So a equal to minus kb square. Okay. So there are two ways to move forward. One is to directly to find the distance from this equation. That is a shortcut if it will be asked. And another way are two-step process. So first I'm going to show the two-step process. So here A can be written as dvdt. So if I write in the place of A that is dvdt, so dvdt is minus kb square and bringing the v in the left side and keeping the minus sign in the right side. So it becomes dv by v square equal to minus k dt. So taking integration, so taking integration is dv by v square minus k dt plus c. So from this, the formula that is x to the power n dx equal to x to the power n plus 1 by n plus 1, where n not equal to minus 1. So here is n not equal to minus 1. Here is the n value is minus 2. So I can write that is minus 1 by b minus kt plus c. So now it is the moment to use the initial condition. So initial condition at equal to 0, v is u. So if I put in the place of v that is u in the place of t that is 0. So this first term is 0 that is c. So c becomes minus 1 by u. If I put the c in this equation, I will get minus 1 by v minus kt minus 1 by u. So it becomes 1 by v equal to ktu plus 1 by u. So v becomes u by ktu plus 1. Right. So this is the velocity, instantaneous velocity at any instant of time of the particle. And it is easily visible that since our k is a positive constant, so as long the time is increasing. So that is, if the t is increasing, then the v is decreasing, right? With the time. Okay. So next, we are our turn is to find the distance. So writing the for the dx dt, I am writing v as dx dt because it is moving along x-axis. Right? Then again, multiplying with the dt from both sides, it becomes ktu plus 1 into dt. Taking integration, okay. So it becomes dx equal to u ktu plus 1 dt plus c. X becomes dx becomes x becomes u, and this integration 1 by ktu plus 1 dt plus c. So i- this type of integration I can write, that is, in the place of ktu plus 1 is z, and after taking differential both sides, so it becomes ku dt. It is the usual method. I am not going to. So if you can understand what is going on in this step, then please differentiate the both side with respect to t. So it becomes 3z dt equal to ku, because the derivative of the one is 0. Then dt equal to, so it becomes a ku dt equal to dz. What I have written here. So dt becomes dz by ku. So now I'm going to put all the things. So x becomes u in the place of ktu plus 1, that is z, in the place of dt, that is dz by ku, and plus c. Since u is constant and non-zero quantity, so u will cancel. So it becomes simple dz by z plus c with a 1 by k factor outside of the integration. So x becomes 1 by k ln z plus c. So that is the way to get the value of the distance at any instant of time. So x becomes 1 by k ln, what is z? Z becomes, we have picked the z, so z here ktu plus 1. So that is ktu plus 1 plus c. Our last task is to find the integration constant, putting the initial coordination. So at t equal to 0, it is taken that x. We have found, we have put here initial conditions. So x is x naught here, right? So at t equal to 0, that is x is x naught. So I'm putting in the place of x is x naught 1 by k, that is ln 1 plus c. But ln 1 is 0, right? Because when I will put t equal to 0, this term becomes 0. That's why it becomes ln 1. So ln 1 is 0. So that is c equal to x naught, right? So the final expression, so x becomes 1 by k ln ktu plus 1 plus x naught. Yeah. So that is the expression of the x. So it is easily visible that from the logarithm or log behavior, that when t is increasing, that is x is increasing, right? So can you see a very surprising result? Surprising result is that the velocity we have found when the t is increasing, v is decreasing, but when the v is decreasing, this t is increasing. Sorry, the distance will increasing. So it is very surprising case, right? The particle will never stop anywhere. So it will stop at infinity because it is, so the log. So this is a very surprising result. What is going on actually, the physically actually the physical significance of this picture is when the t is increasing, the velocity is decreasing. If the velocity is decreasing, the force itself, that is k minus mv square, is actually the decreasing because of v is decreasing, right? So, so at the that is why the force becomes okay, less negative, and hence the particle is moving towards x and going to infinity because there are retarding force control is decreasing. It is being accelerated instead of deaccelerated after some time. So that is really happening here. So that is a very surprising case, and this is the way to analyze this. So I'm going to write that. So when t is so the force become decreasing. If the force become decreasing, that means the particle can reach a very long distance with diminishing velocity. Okay. So let us take another case. So we have analyzed this case we have found. So I have to show you another result. I have to move to another from another direction to get the distance very easily. So if we write in the place of a dvdt, we have written a equal dvdt, but this can be written as dv dx dx dt, and dx dt itself is v, so v is dv dx, right? So there is another way to express the acceleration in this way, and if I put that in the very beginning, that is a equal to minus kv square here. So we can escape the substitution of variable method. So it is very easy. So v becomes this. So that is dv by v equal to minus k dx. So if I integrate that, right? If I integrate that, so that is dv by v minus k dx plus c. So dv ln v minus kx plus c. So at in this way, when the log or the ln or log any log is appeared in the left side, there is a trick to express the constant, this constant, integration constant in terms of a log of another constant, that is ln a say. So I am taking the ln a in the left hand side, that is ln v minus ln a, that is minus kx. So v by ln a minus ln b is ln a by b. So I have written ln v by a minus kx. Yeah. So it becomes v equal to a e to the power minus kx. Okay. So this actually gives a very important result, which actually opens the uh, f- meaning of the physical significance. It discloses the minimum the physical significance of this whole thing. It is telling that at this v becomes zero, the v can become zero only at infinity, right? Because the e is greater than 2 and less than 3. So v can be zero only at x tends to infinity. Otherwise, it cannot be zero. So the particle will never stop. And we have already seen the why is it so? Because the force is decreasing continuously with the velocity because the velocity is decreasing with the distance. Okay. So that is why the force is decreasing with the distance, and the particle got actually the kicks at every time with the distance to move forward, but with the diminishing velocity. Okay. So this was So if I plot the graph with the v, then the graph will be looking like this. It is the exponential decay curve, right? So that is here v equal to u. How do you know the v equal to u? So at we have already told that at equal to 0, I should write a graph properly. So I should draw the graph properly. It is not a right way to draw. So let me put the initial condition first. So it is said that from the very beginning that at x equal to x naught, the velocity is v equal to u. So I'm going to put that here in the place of v, that is u, when the value of x naught. So a becomes u into e to the power k x naught. Okay, so if I put that, so v becomes u e to the power. Thus I'm putting the a in the place of this above equation. So it becomes a e to the power minus kx. Now I'm writing u kx naught minus x. So it becomes, I can write this, it is u is minus k x minus x naught. Simple. So that is the solution. Okay, so now I'm going to draw this in a graph. What should be the graph? So that is, suppose it is x equal to x naught. So after that, so this is the initial. So right now, and from that, the curve will be decreasing. It is slightly more curve. Yeah. So this is the plot, and here the value of velocity is u, the initial position. So this is a very surprising case. So this can be occurred. So it is already, it can open your eye to see that a particle can go to the infinity, a very long distance, with a diminishing velocity value. It needs not to be stopped. Okay. Next thing, we will take a very other example. We can take the other example. That is when I have taken the case number two, a very easy case. That is when the n value is one. So if I take that is minus kv to the power n. So now that is simple minus kmv. So here this can be solved in a very simpler way. Let us do this. So if I write k, if can you recognize what is mv? Mv is the momentum, right? Linear momentum of the particle at any instant of time. So I am writing that is simple kp. That is p is equal to mv, right? From the Newton's law, I can also write the f as dp/dt. So dp/dt is equal to minus kp. Hmm? And now I can write this integration. So this integration is much more easier to deal with. So that is minus k dt. It is a shortcut to do this. So now I'm going to integrating this equation is dp/dt. So k dt integration. So that is c. So integration dp by p is ln p minus kt plus c. So our task is to find what we have to find the velocity of the particle at any instant of time. So again, we have seen that there is a log here. So we have to express this in terms of the log, that is ln A say. So ln P minus KT. plus ln A. So it becomes ln P minus ln A minus kt. That is ln P by A equal to minus kt. That is P by A e to the power minus kt. And P becomes e to the power minus kt by into A. And P is mv. So that is A e to the power minus kt. V equal to A by M e to the power minus kt. So that is a velocity, but m is constant, A is constant. I can write the constant by constant, another constant. I can express that. So I can express it as B constant, say B e to the power minus kt. So B is A by M, and that is the solution of the velocity. So it is done. So now we are going to find the B itself. So at with the initial putting the initial condition. So at t equal to 0, so V is U. So if I put here U equal to, so B e to the power 0, because I'm putting k into 0 here. So B is equal to U, because e to the power 0 is 1. So B equal to e to the, so it becomes B equal to U. So U into e to the power minus k. Yeah, so that is the solution. So it is decreasing velocity. Again, we have found a decreasing velocity. So let us find the distance. So I'm writing in the place of v dx dt. So dx dt is u into e to the power minus kt. So that is dx equal to u e to the power minus kt into dt plus c. So integrating both sides. So that is x becomes u and it becomes e to the power minus kt by minus k plus c. Why? Because integration of e to the power mx dx equal to e to the power mx by m, right? Plus c. That is why. Okay. So, so I should write the alphabet properly so that you cannot be confused. That is k. Yeah. So x becomes minus u by k e to the power minus kt plus c. So at equal to 0, x equal to x naught. It was the initial condition. So if I put here at equal to 0, so e to the power 0 becomes 1. In the place of x naught, it is u by k plus c. So c becomes, so c becomes x naught plus u by k. So I'm going to put it in the last here to get the value of x. So x becomes minus u by k e to the power minus kt plus x naught plus u by k. So it becomes u by k 1 minus e to the power minus kt plus x naught. So that is the final expression of the distance it will travel in time t. Okay, so its velocity is decreasing. Hmm? So um, now the question is, what is the distance it travel before it being stopped? In the initial case, we have found that if when the f equal to minus kb square, so before it will stop, it travels infinite distance. But when we are considering the F equal to minus kmv, then what will be happen? So we have found that it's V equal to u e to the power minus kt, right? So u becomes 0. So sorry, the V becomes 0. When V becomes 0 again, you can see that it is E is a quantity greater than 1. So it can be 0 only at t equal to infinity. So at t equal to infinity, tends to infinity, I should say, B tends to 0. So if I put here t tends to infinity in the place of distance, so distance was x equal to x naught plus u by k 1 minus e to the power minus kt. So if I take that limit t tends to infinity, xt, it is x naught plus u by k limit t tends to infinity, 1 minus, sorry, yes, minus kt. Then this part is k, e to the power minus infinity. It becomes e to the power minus infinity. Then it becomes 0. So it becomes 1. So answer is x naught plus u by k. So can you see that this distance is now finite? So to say, so if we will reduce the power of n, we will reduce the power, that is initially it was power of 2, right? So when the initially we have considered f equal to minus k mv square. So here the power, if the power is 2, the distance become infinite before it being stopped. But now when it is minus kmv, the power, there is a, I have reduced one power, right? So it becomes x is finite quantity. In the both cases, the velocity is decreasing, right? Okay, so in the both cases it has been decreasing. But in the previous case, the x become infinity. In this case, it becomes a finite quantity. Why it is so? Can you recognize why it is happening? Because of one answer is that if you the power, here is the power is same, that is a v square. So if the v is decreasing, the square of its quantity is decreasing more and more and more. So the f is reduced uh, of, with a greater value than the latter case. So that is why when the force is being reduced in the previous this case when the came v square, okay, so if I take the magnitude of the two forces and get the ratio, suppose I'm going to write that is f1, that is f2. So that is f1. If I take the f1 by f2, so simple it is v. Right. What is what does it tell that f1 is, if I decrease the f1, right, then it will be decreasing heavily with the velocity because it has the power of square. So if I take v to the power cube set, you can easily imagine what will be happen. The same thing will be happen, right? So it will be decreasing more and more and more. So the force will be reduced more and more and more with a decrease with the velocity. So the effect of the force in the previous case will be being reduced more than the latter case, where it is actually moving with a dragging force just proportional to its velocity itself, instantaneous velocity. So that is why when the power is becoming if we consider the powers of the velocity which is greater than one, the result will be different. When the power is one, then the result will be surprisingly opposite to the these cases. So the conclusion is when you are considering the power in is greater than one, I'm taking n is the integer, you are taking is one greater than one. So that is that force, the dragging force, I should say. So dragging force actually work, but dragging force is reduced with decreasing with the decreasing velocity, with a decreasing velocity. But since the power n is greater than one, the f is being reduced heavily. That is very very important distinction between the two cases. Okay. What will be happened? Can I go further? So what will be happened when the power is now k v to the power half? It is now less than one. I have taken minus k m v to the power half, right? So it becomes, so what will be happen? So let us see. So s equal to that is again m. Now I cannot write the dp dt because now the left hand side is not. So you can actually you can if I write so again I can write that is m, that just the right side root m into root m. So that is m v to the power 4 halves. That is minus root m. That is p to the power half. P is the momentum. So that is dp dt. So it becomes dp by p to the power half, right? That is minus k root m dt. So integration will give me, what is the integration? It will give me that is 2 p to the power half. Just I have skipped one step, t plus c, and it becomes, so the v will be decreasing, right? We have already anticipated that v will be decreasing. Just remember that remember that. So that is it becomes, so at t equal to 0, so first we have to express that mv to the power half. That is k root m t plus c. So for shortcut, I can write the c as some constant root m into some, because the constant can be written in terms of the multiplication of any two constants. So I can write the root m into say a. I am writing this because the root m factor will be gone from the both sides. The shortcut to get this, so that is root m t, that is root m a. So root m will be gone. So it becomes v to the power half, that is minus k by 2 t. plus a by 2, right? A by 2 I'm writing b. Yeah. So, right, now at t equal to 0, so v is u, initial velocity, so that is e to the power half b. So it becomes v to the power half minus k by 2 e plus v by half. So it is decreasing, so that is v equal to u to the power half minus k by 2t square. Okay. So it is decreasing, decreasing. So yeah. So this is the velocity again. With the time, it is decreasing from the initial velocity. Okay. So what is the distance it will travel? So can I find the distance from here? So it will be your home task to find the distance. So it is a home task to find the distance it will travel. Okay, it will travel before being stopped. So can you see that when the I can find the time when it becomes stopped? So it becomes stopped when it becomes stopped when the v becomes 0. That means that is u half is k by 2 into t. So t equal to 2 u half by k. So that is the time when the particle being stopped. But we have to find the distance when it being before being stopped. What is the distance it will travel? Will it be finite? Will it be infinite? Okay, let me stop.